Harvey. I'm coming to you guys from eastern Idaho, in Idaho Falls. So this is my recording of my final project. So what I've done is a point pattern analysis. It's a very simple GIS technique where you analyze how points are dispersed along an area. Here's a quick picture of what I'm talking about. Here's your study area, and this is an example from Wikipedia of just four patterns of points, 256 points. This is considered clustered within the area. This is normal. Random points are sort of evenly or distributed either further and closer together. And then regular is a completely even dispersion across the study area. So, like I've probably told you guys a lot, most of my reason for taking this class is to be able to do GIS techniques in free and open source software, mostly because my personal beliefs for open source software, and a lot of GIS jobs these days are asking for qualifications, experience using R and Python and things like that. So I'm really glad that I got the ability to do that in this class. But I did have to use a little bit of GIS to get my data set up. So here's what I'm using. This is the tax lots in Washington County. I touched it, and of course it's huge. There are there are over like 400,000 tax lots. And what I did was I converted the area of the tax lots. You can see this is Highway 26. This is Highway 217. This is Beaverton. I think Hillsborough Airport's right there. So these are the tax lots in background of the data. I converted tax lots in Washington County into points. There are over 400,000 points, and I sorted them by the assessed land value. My question for the entire project is, are the tax lots with the highest land value clustered or dispersed? And so it's just a simple point pattern analysis method. In order to do so, I had to take out the highest valued tax lots, which I'll show you here. So there's 200 something of them, and they're kind of all around the county. I can zoom out here. You can kind of see an outline of our study area here. So I had to bring this into R, which is my favorite part. So point pattern analysis using R. So right in the beginning, you have to load your libraries that you're going to use. We're going to use RGDAL, which is a spatial data package that brings spatial data into R. We're going to use SpatStat, spatial statistics, and Lattice, which helps us make a graph here at the end. Some of the tutorials I was using on the internet, this guy made this function that converts kilometers to degrees, which will be helpful in a little bit here. Okay, so loading the data set into R. This is my favorite function. It's read OGR. That's from the RGDAL package. You point it to your shapefile stored on your computer, and brings it in. We've got and it brings it in the class spatial points data frame, which we can look at a little bit. It's got the 200 points I pointed at, or I showed you earlier, but it also has all of the attributes that come along with the points. We've got the owners, the land value. That's particularly what we're looking at right now. Building square feet on there, sales date, stuff like that. Very cool. And that's data that I grabbed from the Portland Arliss website. It's free. You can just download it. Okay, so in R, we take this special shapefile and break it down into just a very simple point coordinate matrix, which makes everything very easy. We've taken the lat-long coordinates from our shapefile. We just turned it into a matrix, and we can look at that right here. Let's see, I plotted it. Looks pretty good. So it looks like what it looked like in ARC, which is perfect. We've got our latitude around 45 degrees, a little higher than 45 degrees, longitude Let's see, let's compare that to arc. You can see it looks very similar. Okay, so in order to do a G function test, we need to test it against some random points. So we're going to create some using these two objects right here. And what these do, let's see, let's run them. There, we've got UX and UI. So what it does is it creates a bounding box around our tax point object, which is our matrix of our tax lot points. So the bounding box is basically where this box is here. It just takes the maximum and minimum lat long, creates a box, and then fills it in with points. So let's see what that looks like. There, so random. We've got our latitude here, and it doesn't really show longitude, but you can see they're randomly spaced, which is good. And then we also want to create some regularly spaced points to compare our data set with. Let's make some of those, and let's see what the regularly spaced points look like. There we go. See, so they're evenly spaced. This is the opposite end of the spectrum. So this should come out. We'll be able to compare our data set with these. Let's see here. Okay, so let's plot. Oh, this part of the script is really cool. I've already showed you with the basic plot, but this one plots them all kind of in together, but it sort of takes away the spatialness of it. The points don't really look like they did before. There's that weird outlier over here, I think. But so we've got the tax lots with the highest land value. We've got our random points, and we've got our regularly spaced points. It's not so useful when it's not sort of in like map shape, but them together because it's squished. But it's nice to compare them next to each other. Okay, so we're going to perform the G test. Let's make the G test on the data itself. We'll run that, and it creates this env object, this envelope function with this PPP function, which is a special data type for the SpatStat library, and it's it creates a bounding box around our data set, and it runs this G estimate. And so let's do it for the random points as well. Run that. Then it does this 99 permutation simulation thing, which yeah, let's see here. Let's do it for the regular points. And I've been getting this error. I've been working on this for a while, and in the regular points, a few of them lie outside the specified bounding box window, which I'm not really sure about. If you go back here on the plot, I think that maybe they might be sort of outside the boundary. And I was looking at the tutorial I was sort of following. They have this jitter function, which I really enjoyed, because what it does is it instead of just making a completely exactly square points, it adds in a slight bit of difference between them. Jitter is what it's called. That might be messing with it. I'm not sure. I have to go back, maybe, or leave it as it is and see how it all works out. So let's see. We've got back to we made the ENVR. That's good. The G test. We're going to make this G test. So we're going to combine everything we've done, the ENV, the ENVR, the ENVU, and put it all together in one G test object. There it is. And we can look at the G test here. Let's look at the G test object. And we can see it has the R value, the observed value, the theoretical value, the low, the high, and what it is. And then I think if you scroll down, that's top tax lots. If you scroll down really far, it'll load, and we were right on the break from top tax lots to random pattern. So they're all in there in one big pile. So let's see, go back to, okay. So now that we've got the random data set, the normal data set, and our real data set, let's plot them all together. At the very end, we have the XY plot of the G function, and what this shows is all three, or the G-test, basically, which is all three of the ENV data sets put together. What this is showing is the observed versus expected value. The straight line in the middle is the random data set. This line right here is the normal data set, because they are the same the points are the same distance from each other all around the entire study area. And then the final one, which is our real data set, let me draw on it, which is kind of fun. Let's see here. Draw red. I can't draw. There we go. There's our data, real world data from tax lots in Washington County. This X bar is considered distance. So what this means, since it rises rapidly early and tapers off at the end, is that at shorter distances, at shorter total distances, the overall distance between the points is less. So our data set is considered clustered, which makes sense if you look at the stop drawing. If you look at it in ARC, and the drawing is still there. If you look at it in ARC, the points are sort of near each other, but the actual study area, I think this will point it out a little bit better. If we go back to this, where is it? This plot. Consider the box here our study area, because it covers all of our points. They're all sort of together, and so the end result is they are clustered. I made a second little plot here. Let's get our drawings out of the way if we can. Clear all. Perfect. Okay. Nope. Clear all. Stop drawing. Okay. So I made these, which kind of show it in a different way, which is nice. Let's see. Plot ENVU. So at shorter distances, they are shorter overall, but this is our error. The G observed is that black line. And if you see this one doesn't work. The regularly spaced ones, here I'll show you, it breaks it. It doesn't like to plot it, and the error is argument should select 2 columns of X. I'm not really sure why that happens. It plots the other one perfectly and it looks great, and it plots the last one, which is our real world data, very well. Here it is. So this is expected based on the study area, and this is observed, which shows that at, basically halfway here, at lower distances overall, the points are more together, and so we have a clustered data set. The final answer is that the higher valued tax lots in Washington County are more clustered than not clustered in the entire for this area. I believe if we included the entire Washington County as the area, the answer would be they'd be even more clustered, a little more so than we were observed, because these tests are very specific about or are very dependent on the area. So if the area is this, we get a completely different answer than if the area was this. And that's just a basic rule of spatial statistics. It's something that we have to deal with in the field, and it's just an interesting problem to have. So there's my R project. Let's stop drawing, go back here, and thank you very much. I'm going to have this up on the board, on the blackboard, and so everyone can play with it. Have a good rest of the term, everybody.